All right, so we're going to evaluate a double integral over a region D, which is not a rectangle this time. The region D is described by this set. It's a set of all points x, y, such that y is between 1 and 2, so it's a fixed interval, and x is between y minus 1 and 1. So we're thinking of x as being bounded by functions of y. This just happens to be a constant function of y. That makes this a type 2 region. This is one of the somewhat rare examples where I don't really need to worry about graphing anything because I can use the set as it's written. This double integral we want to write as an iterated integral, and whichever of my two intervals here, the interval for the y and the interval for the x, whichever one has constants, that makes it a fixed integral. That's going to be the outer integral every time. So this is going to go from 1 to 2 here. And then my inner integral is going to use these as its limits of integration, y minus 1 and 1. Y minus 1 and 1. The function that we're integrating looks like 2x plus y. Now, remember the dA has to become either a dx dy or a dy dx. And don't try to memorize which one you use for a type 1 region, which one you use for a type 2 region. Just remember the inner integral, which has these limits, that's the interval for my x. So notice that the x is sitting between those two values. So that means I need to use a dx first, then the dy will come last. Okay. Now, if I'm integrating this with respect to x, my 2x is going to become an x squared. Y is being treated like a constant, so I get plus yx here. And we evaluate that from y minus 1 to 1 dy. Now I have to actually plug these things in. So notice this is going to look like this. Integral from 1 to 2 of... So if I plug a 1 in, 1 squared is 1. And if I plug a 1 in for x here, remember these are x values, I just get a y. So I get 1 plus y after plugging in that 1. 1 plus y minus, now I plug the y minus 1 in, and remember again that y minus 1 is being plugged in for the x's only, so this becomes y minus 1 squared plus y times y minus 1. Lots of parentheses and things to worry about. Okay. Clearly, we're going to want to simplify that down to make the integral much easier to evaluate. So this integral from 1 to 2, after doing a little bit of algebra on this, this simplifies kind of nicely, actually. It simplifies down to negative 2y squared plus 4y dy. Okay. Now, of course, this is a polynomial. This is pretty easy to evaluate. I can pull a negative 2 out, for example, and then just integrate what's left. Notice y squared minus 2y is what's going to be left. And if I were to integrate that, we're going to have y cubed over 3 minus y squared. And that goes from 1 to 2. And then that's easy to evaluate. It's just arithmetic from here. This one should come out to 4/3. Okay, so not so bad. But the key difference here was that the inner integral had, for its limits of integration, functions of y instead of just constants. And so when we got to this step here, after performing the inner integral, we were substituting in functions of y. That makes this integrand potentially look a lot more complicated than it would for a problem in 15.1. So it's important to simplify that down as much as possible before we start to evaluate the next integral in the line. Let's try another one. Okay, this time we're not given the description of D as a set, so we have to come up with that description. D is bounded by y equals x minus 2 and x equals y squared. So notice one of these, y looks like a function of x, and then the other x looks like a function of y. We don't want a mix of those two things. We want everything as a function of x or everything as a function of y to make it either a type 1 or a type 2 region. So This is a little bit more typical of an example where we want to sketch the region out first to figure out what we want to do with it. Let's start by graphing these. So let's see, it's going to look like this. Y there, x there. Okay, y equals x minus 2. So that's a line with a y-intercept of -2. Slope of 1, which means it's going to come up here to 2. And do something like that. Okay. And then here, x equals y squared. That's a parabola opening towards the right. So, and no, this is not going to be drawn perfectly, but should just be a rough sketch so we can work with something. You can see that these two curves bound this region right here, right? Now, if I were to treat this as a type 1 region, which is bounded by two functions of x, then I have this part of the parabola would pretty clearly be seen as the top function or the highest function. But then both the parabola and the line, depending on which part of this region I'm in, can be treated as the lower curve. And that's a little bit more complicated than I want to make this problem. Notice it's actually easier if we treat this like a type 2 region, because type 2 region, x is bounded on the right by this function and on the left by this function or this parabola. So that's easier to describe. I'm going to treat this like a type 2 region. If we call this D, I want to try and describe D as a set the way we've been seeing it. Now, in order to do that, if I'm treating this like a type 2 region, then both of these curves need to be thought of as functions of y, not functions of x. So I already have my parabola as a function of y. It's x equals y squared. This line right here is originally presented as a function of x, but it's easy enough to solve this for x and write x equals y plus 2. So now both of those are being thought of as functions of x, or sorry, functions of y. So that means if this is the rightmost function and this is the leftmost function, then x is sitting between these two. Y squared is less than or equal to x, which is less than or equal to y plus 2. Be careful to make sure you have the correct function on the correct side here. You don't want to mix these up. Okay, then we need a restriction for y. Well, our interval for y is going to come from where these two graphs intersect. Okay, I need to determine those two y values. That's pretty easy to do because it's just a matter of taking these two functions and setting them equal to each other. Y squared equals y plus 2, and then solving this as a quadratic. This is really easy to solve. We end up with y equals -1 and 2. That corresponds to these values here, -1 and 2. Okay, so that's what's going to give me the interval that I use for y. -1, y, 2. It's important to write this set out when you do these integrals. It's oftentimes kind of tempting to just go straight from the picture to your iterated integral. But I'd suggest practicing this because this is going to be more useful the further we get through chapter 15. All right, but now that we have that, let's go ahead and set up the iterated integral. So again, this is another type 2 region type of example. So that means my fixed interval here is going to show up on the outside. We're integrating from -1 to 2. The integral where my bounds are y squared and y plus 2 will show up here. Y squared, y plus 2, and then the function I'm integrating is y. Remember, my dA is going to become dx dy. And again, if you're forgetting which one goes first, look at your innermost integral, go back to and see which variable is sitting between those two limits. It's the x. So the dx comes first, followed by the dy. Okay, now if I'm integrating with respect to x first, y is being treated like a constant, and so this will look like the integral from -1 to 2 of yx from y squared to y plus 2 dy. Okay. Remember, we just integrated with respect to x. Those are x values. And so this integral goes from -1 to 2. I'm plugging these in for x. So that's going to give me y times y plus 2 minus y times y squared. It's my kids screaming in the background. So we want to simplify that down. This one comes out also just a polynomial, which is convenient. We like those. So we're integrating from -1 to 2. This one simplifies down to, what do we get for this one? Y squared plus 2y minus y cubed dy. Okay. Now, again, from here, it's kind of just calculus 1, calculus 2 stuff, evaluating the integral, definite integral of a polynomial. So nothing tricky about that, so I'm going to let you fill in those gaps. But this one, when you work through everything, comes out to 9/4. Okay. So there's a couple of examples. We'll do some more in the next video.